Picture a line of freight trains loaded with plastic bottles, bags, packaging, containers. Stretch that line until it circles the entire planet 7 times. That's how much plastic the world produces in a single year. 430 million metric tons. And here's the part that should worry you. Less than 10% of it has ever been recycled. The rest is still out there, broken down into smaller and smaller pieces, but never gone. Microplastics now show up in human blood samples, in lung tissue, in the walls of arteries. The material we built modern life on is quietly dismantling it from the inside. For decades, scientists have tried to replace plastic. They've failed. Not because the alternatives don't exist, but because none of them work at the scale the world demands. Bioplastics crack under pressure. Starch-based materials dissolve in water. Plant fiber composites cost too much or need farmland we don't have. But in October 2025, a research team at Northeast Forestry University in Harbin, China, published something different. A material made entirely from bamboo that matches the strength of conventional plastic, biodegrades completely in soil within 50 days, and can be manufactured on the same equipment factories already use. No oil, no new infrastructure, no compromise on performance. They call it BM plastic. And if it scales, it could end the plastic age. Before you understand why this matters, you need to understand why plastic won in the first place. It's not just cheap. It's the only material in history that checks every box at once. Plastic is moldable. You can shape it into anything from a syringe to a car bumper using the same basic process. It's durable enough to hold chemicals that would eat through metal. It's light enough to cut shipping costs in half. It doesn't rot, it doesn't rust, it keeps food fresh for weeks and medicine sterile for years. Try to replace plastic with glass, and your shipping weight triples. Try metal, and your costs explode. Try paper, and moisture destroys it. Try any natural material, and bacteria start breaking it down the moment it leaves the factory. That durability is exactly what made plastic indispensable. And it's exactly what's killing us now. Because plastic doesn't break down. It fragments. A bottle becomes 1,000 pieces. Those pieces become 1,000,000 particles. Those particles become dust that enters soil, water, and eventually, blood. Scientists have found microplastics in placentas, in the deepest parts of the ocean, in Arctic snow, and every solution scientists have tried has hit the same wall. PLA, the bioplastic made from cornstarch, feels like progress, until you realize it only biodegrades at industrial composting facilities that maintain temperatures above 58 degrees Celsius for weeks. Toss it in your backyard compost or a landfill, and it behaves like regular plastic. PHA, made by bacteria that produce plastic-like polymers, biodegrades anywhere. But it costs several times more than conventional plastic because growing bacteria at industrial scale is expensive and slow. Starch-based plastics dissolve in water. Cellulose films crack under stress. Every material that biodegrades easily is too weak. Every material that's strong enough doesn't biodegrade. The problem isn't finding a plant that could replace plastic. The problem is chemistry. Plant fibers are held together by hydrogen bonds, weak bonds. If you try to mold them like plastic, they fall apart. If you add binders to hold them together, you're adding petroleum-based chemicals, which defeats the purpose. If you don't add binders, the material cracks under pressure or absorbs water and swells. For 50 years, that's where the story ended. Then in 2023, 2 researchers named He-Ching Wu and Dawei Zhao started looking at bamboo differently, not as a fiber to bind together, but as a molecule to rebuild. Bamboo is almost pure cellulose, long chains of sugar molecules locked together by hydrogen bonds, the same bonds that make it weak. Wu and Zhao realized that if they could break those bonds without destroying the molecules themselves, they could rearrange them into a stronger configuration. They developed a 2-step process. First, they soak bamboo cellulose in a solution of zinc chloride and formic acid. The acid slips between the cellulose molecules and breaks the hydrogen bonds holding them in their natural structure. It's like untying a bundle of rope without cutting the fibers. The molecules stay intact, but they're no longer locked in place. Then they add ethanol. The ethanol acts as a guide, nudging the freed cellulose molecules to rebond in a new pattern. Tighter, denser, aligned in a way that nature never arranged them. What comes out is a solid material that looks like plastic, molds like plastic, and performs like plastic. but it's 100% bamboo. No petroleum, no synthetic polymers, just plant molecules rearranged at the molecular level. They published the results in Nature Communications. The numbers made people stop. BM plastic hits 110 megapascals in tensile strength. That's about twice as strong as PLA and stronger than high-impact polystyrene, the plastic used in disposable cups and protective cases. Its flexural modulus, the measure of how much force it takes to bend something, reaches 6.41 gigapascals. That beats ABS plastic, the material in car dashboards and Lego bricks. Heat resistance? BM plastic survives temperatures above 180 degrees Celsius. The research team baked test samples at 100 degrees for 7 straight days. No cracks, no warping. Work of fracture, the energy needed to break the material, hits 80 kilojoules per cubic meter, higher than conventional plastic, higher than most bioplastics. But here's the part that separates BM plastic from everything that came before it. Bury it in ordinary soil, and it's gone in 50 days. Not broken into smaller pieces. Gone. Fully biodegraded by naturally occurring soil bacteria. And if you don't want to bury it, recycle it chemically. The process recovers the cellulose molecules and reassembles them into new material that retains 90% of its original strength. Conventional plastic loses strength every time you recycle it. BM plastic barely fades. The researchers ran one more test. They took BM plastic, molded it using a standard injection molding machine, the kind every plastic factory already owns, at room temperature. It worked. No special equipment, no high-pressure chambers, no retooling required. That last part matters more than the strength numbers. Because the graveyard of failed plastic alternatives is full of materials that worked in the lab but died in the factory. Materials that needed custom machines. Materials that required temperature control so precise that manufacturers couldn't risk production at scale. Materials that biodegraded so fast they broke down on the warehouse shelf before they reached the customer. BM Plastics sidesteps all of it. The chemicals used in production are common and cheap. Zinc chloride, formic acid, ethanol. The ethanol is even recyclable within the process. Early cost estimates put BM plastic production at around $2,300 per ton. Conventional plastic costs $1,200 per ton. That gap sounds like a problem until you realize what it doesn't include. Conventional plastic costs $1,200 per ton. That gap sounds like a problem until you realize what it doesn't include. The cost of cleaning microplastics from water systems, the cost of removing plastic waste from oceans, the medical costs of treating conditions linked to microplastic exposure. A study published in 2023 tried to calculate the true cost of plastic when you factor in environmental damage and human health impacts. By 2040, that number could hit $2,400 per ton. Suddenly, BM plastic isn't more expensive, it's cheaper. And it gets cheaper still when you consider what it's made from. Bamboo grows faster than any other plant on Earth. Some species add more than 1 meter of height in a single day. Cut a bamboo forest, and it regrows from the same root system in 3 to 5 years. A pine forest takes 25 to 30 years. Bamboo produces 5 times more plant material per hectare than conventional timber. It doesn't need replanting. It doesn't need fertilizer. And it grows on land that's too steep or too poor for food crops. China holds more than 7.5 million hectares of bamboo forest spread across 20 provinces. 500 different species, an existing supply chain that already supports over 7.5 million farmers and generates close to 320 billion yuan every year. The infrastructure is already there. The harvesting equipment exists. The processing facilities are running. The logistics networks are built. BM Plastic doesn't need to create a new industry. It plugs into one that's been operating for decades. And China isn't the only place with bamboo. Total global bamboo forest area sits at around 22 million hectares, scattered across Asia, Africa, and South America. Countries that have spent years watching plastic waste pile up in rivers and coastlines now have access to a feedstock that grows in their own territory. This is where the story stops being just about material science and starts being about geopolitics. In 2022, China launched a national plan to replace plastic with bamboo-based materials. A year later, they followed it with a 3-year action plan, laying out specific targets and timelines. By 2025, bamboo fiber tableware exports jumped 35%. Cities began replacing steel and cement pipes with bamboo composites. A drone manufacturer built a test aircraft with 25% bamboo content. It weighed 20% less than the carbon fiber version and cost 1/4 as much. China isn't waiting for the rest of the world to agree on a solution. They're building the replacement while everyone else is still arguing about the problem. And the rest of the world is still arguing. In 2024, global plastics treaty negotiations collapsed. Countries couldn't agree on production caps, couldn't agree on waste management standards, couldn't agree on who pays for cleanup. The regulatory path to solving plastic pollution is stalled. That leaves the market, and the market moves when someone offers a product that works better and costs less. BM Plastic has a shot at both, but it's not there yet. The material is still rigid. It works for bottles, containers, structural parts, anything that needs to hold its shape. It doesn't work for plastic film, for thin bags, for any application that needs flexibility. That cuts out a significant portion of the plastic market. And then there's the durability question that runs in the opposite direction. BM plastic biodegrades in 50 days once it hits soil. That's the goal. But what happens during the months or years it's in use? Does it start breaking down on the shelf? Does humidity trigger early degradation? The research team ran stability tests, and the material held up. But 50 days in a lab isn't the same as 5 years in a warehouse in Mumbai or a shipping container crossing the Pacific in summer. The biggest challenge isn't technical. It's scale. Moving from a university lab in Harbin to factories producing millions of tons per year is an engineering problem that has broken more breakthroughs than any chemistry ever did. You need supply chains that can deliver bamboo cellulose in consistent quality. You need manufacturers willing to risk production lines on a material that's never been tested at volume. You need customers willing to pay a premium before economies of scale bring the price down. Every one of those problems is solvable, but solving them takes time, capital, and a willingness to fail repeatedly before it works. The question isn't whether BM plastic can replace conventional plastic in theory. The question is whether someone will pay to find out in practice. And that question is being answered right now in Chinese factories, research labs, and supply chains that most of the world isn't watching.